That would be great as it goes into.
Okay. Sure. I will not make it full screen till.
Okay, fine.
Oh, well, it is probably full screen. Do you see the slide?
Yes.
Full screen, right?
Yeah.
Oh, okay. Okay. Yes, sir. Yes.
Okay. Okay, so I will actually record this as well because there is some issue with the YouTube stuff. It's not public yet, so I'll just keep this in my computer as well. Okay, so it's a pleasure to host another Wednesday colloquium session, and especially as we are doing a series of colloquia on Professor Steven Weinberg, one of the greats in physics, who recently left us for a heavenly abode, I hope. So, we have today Professor Urjit Yajnik from IIT Bombay, who is going to talk about the cosmology aspects of the contribution of Professor Steven Weinberg. But before Professor Yajnik actually starts his colloquium, I would just like to remind all those who are listening to us for the first time that the NSF Wednesday colloquium is part of a tradition of TIFR started by Professor Homi Bhabha, the founding director of the institute. The idea was to bring along all the natural sciences faculty, be it physicists, chemists, or biologists, under one roof for one weekday, so that we can all listen together. One of the leading scientists in the community giving a talk and enunciating challenging problems in the field. And this has actually helped us coordinate some of the efforts, scientific efforts from TIFR, because collaborations could be started, as well as there could be much wider discussions of the science as such that is presented by the expert. So we are continuing this tradition, and today, of course, we are in this midst of series of colloquia on Professor Steven Weinberg. So I would now request Professor Shirup Rai Chaudhary, who actually sort of started this series with his colloquia on October, the first week of October. So Shirup, could you please introduce today's speaker, Professor Yajnik?
Yes, sure. Okay, it's a great privilege to be able to introduce scientists of the eminence of Urjit Yajnik, and also a pleasure because he's a good friend for many years. Actually, Urjit is a familiar face in TIFR and doesn't really require an introduction, but there are younger members of the audience, so perhaps I should tell you a little bit about him. So Urjit did his integrated masters in physics from IIT Bombay in 1980. Then he went to the University of Texas at Austin in 1986, where his advisor was the very famous ECG Sudarshan. And after that, he spent another couple of years there in Weinberg's group. So whatever you hear about Weinberg today will essentially be from the horse's mouth. And then he was there from 86 to 87. In 1987, he came to TIFR. So that's how long he has been associated with TIFR. He was a postdoctoral visiting fellow here for 2 years. And then from 1989, he has been a faculty of IIT Bombay. And there, of course, he's a senior professor there now. But meanwhile, he has also held important positions in IIT. He was the Dean of Student Affairs from 2011 to 2015. In addition, when IIT Bombay started incubating IIT Gandhinagar, then he was there for 2 years, 2008 to 9, as both Dean Student Affairs and Dean of Academic Programs. He has also been a visiting professor at McGill University and Montreal, at the University of California, Irvine, and also visited many places around the world, Trieste, Perimeter Institute, Germany, South Korea, Japan, China. It's been all over the world and is recognized there. So Urjit works on a multitude of things. He works on unified theories, on supersymmetry, general relativity, cosmology. His work spans particle physics and cosmology and general relativity. The subjects are coming together anyway, and it's nicely personified in his research. So I won't keep you any longer. Let me invite Urjit to come and give us his colloquium on the cosmology part. I have spoken about the particle physics part of Weinberg's contributions, but the cosmology part I have decided would be best done by Urjit, and he can also tell you some stories about Weinberg because of his close association. So Urjit, please.
Yes. So thank you very much to the organizers of the NSF colloquium, such a prestigious forum at which to give a talk, and to the nice introduction and opening remarks by Shrirup. Yes, it's really a great moment we are at this time in 2021. We have lost a great physicist, but he, as well as, of course, some others, stalwarts of that era, we have lost within the past 5 years to a decade. And that marks the passing of an era that was really rather unprecedented in the history of science, and therefore also of mankind. Of course, particle physics has not been alone. There have been front rank research, cutting edge, and developments of extensive developments in many, many directions. But those of us who had the opportunity to be very close to, or rather being inside the arena and getting crushed by the stampede of it, of elementary particle physics and cosmology, it was really the most breathtaking time that we have lived through. And we are celebrating a great physicist's contributions. And as Shrirup has already said, we know him for both the things, for elementary particle physics as well as for cosmology. So this talk is going to be both a tribute to him, but as he would very much like, it should be a tribute to the science, not just his, but of that particular era. And I hope that it will be a inspiration to all the younger people who are listening. Also, it will be peppered with various kinds of personal memories, maybe also some personal opinions, both about science and maybe of society. So it's not a strictly scientific colloquium, as you will, of course, agree. So I will try my best to do justice in this very short time. Preparing this talk was really a flood of so many memories. I already gave one in my own department covering his particle physics. But again, this was a fresh exercise thanks to Shrirup, and I tried my best to cover it well. So that's him. That's Steven Weinberg. And if it looks like a tiger ready to charge, yes, that's exactly how he was most of the time, ready to charge at new physics ideas, to crystallize them and to put them in good use, to elaborate them, explicate them for others, and get them going. So the talk, I will have to build up a bit about antecedents of cosmology, because that's what we are going to talk about. And assuming that there are people in the audience who are not very familiar with it. And then Weinberg's contribution to it, of course, and then his attitude. So Weinberg is not just known for the contributions per se, the technical parts of it, but because physics is such a conceptual subject, we dread the word philosophy of physics. At the same time, there is a perspective on physics, which Weinberg brought to the subject. And I'm sure a sizable fraction of the community agrees with the perspective that he developed, and were probably co-developers as well. So I will try to cover that, and his famous book, The First 3 Minutes, the first popular science book that he wrote, which became a bestseller. And I will try to just highlight why it is a different kind of a popular science book than many others. Okay, so the next bullet point has actually got jumbled. It will probably come first. I will try to also tell you the greatest connection that happened in this past just 50 years, not even a whole century, between the Big Bang universe and grand unification. So we'll talk about that a bit, and then I will try to show some kind of personal memories and pictures. Okay. So I should just cover a little quickly the cosmology before 1964. Why 64 is important, you will see soon. That's when cosmic microwave background was discovered. But back in 1919 and around 1920, within a few years of Einstein developing general theory of relativity, this Alexander Friedman, who was a professor in Russia, developed the solutions that we now use to model the universe. In his solutions, it was very clear that the universe is either going to expand or recollapse. Okay, so I think there's a slide on that. So this is just the outline, that there was an early development, theoretical development, which was not recognized. Then there were telescopes built, which actually found the expanding universe, maybe thanks to the clear skies in the US, which were probably not available to Europe. And then these developments in observational cosmology, C5 variables and Edwin Hubble, and then on to the connection between nuclear and nuclear physics and cosmology. So the thing about Friedman's solution was that he found that either this blue curve, with just the closed universe, which just comes out of nothing, it's a cycloid mathematically, so it just has a singular point at the cusp, or it can keep expanding forever. But if it is expanding forever, then if you go back, then it's going to come out of nothing. So this was conceptually a big problem. Friedman, being a mathematician, probably worried less about it, and sent the papers to Einstein, who was probably embarrassed because he kept quiet about them. And even tried to cover up by saying that there were ways within general relativity that didn't have to happen. But until in 1929, Edwin Hubble drew the straight line, not this straight line, but Edwin Hubble actually concluded that the fact that almost all the galaxies that they had seen up to that point were showing redshift, they were just receding, they were going away. It could be interpreted as an expansion of the entire local universe, because there was a relationship between how far the galaxy was and the speed with which it was receding. So both Leavitt's, Henrietta Leavitt's calibration, which is shown in its modern form here, and Hubble's arduous pursuit of astrophysics. This is the Hooker telescope that he used for most of his observations. Just as a quick side story, Hubble was actually a lawyer. And because of family pressures, which required him to, make money and keep up good lifestyle, he remained lawyer until age 35, when it became possible for him to switch. And then he joined Harvard and became an astrophysicist without any formal training. And then on, just to complete the story of the expanding universe, it became clear then that if you then went reverse, backward in time, then the universe, of course, had to come out of a very small point. It would therefore heat up like any compressed gas. So if you heated up, then there would be way back when nucleons would have to form first, and then they would fuse into the lightest nuclei. So these consequences were possible to calculate because nuclear physics was already emerging in 1930s. And in 1940s, these gentlemen, the ones on the first two on the left, Alpher and Gamow, worked out this primordial nucleosynthesis. And then just to make the author list look elegant, they added beta's name in the middle. So it was called alpha beta gamma paper. But the idea that the universe would go back into very hot origins in super compact form was actually ridiculed at that time. It was, the name Big Bang was coined to make fun of it, not really to describe it. And then on to, we will come back to this later, but Alpher and Herman, then, so Alpher was the driving force in doing another calculation, whereas this stopped with the MeV scale, nucleosynthesis. He later worked out the electron volt scale, 1,000,000, 6 orders of magnitude lower energy, when hydrogen would form, neutral hydrogen would form. So these calculations were done in the 40s and they were just being ignored because most people who were working in cosmology treated it as a philosophical issue, and they were so overwhelmed by the curved space-time and the possibility that all movement was some kind of geometry and so on, that nobody was looking at these practical calculations. Until in 1964, Penzias and Wilson stumbled upon the cosmic microwave background, which would result from this last time that hydrogen was a plasma. After that, it became neutral. And the radiation it emitted was almost uniformly flowing through the sky, across the sky, isotropically and at a fixed temperature. And it was discovered by them, who were electrical engineers. They had nothing to do with physics, but they had a very good apparatus, which was their antenna through which they were actually just trying to communicate. So that is the background in which Weinberg makes his appearance. He was already a professor in the 60s. And there is a unread lecture notes of Weinberg, his Brandeis lectures of 1964, which Weinberg seems to have himself forgotten because he never brought it up. But in his 1964 lectures, which says global and local symmetries or something like some very abstruse kind of lecture, he ends it by saying that now that CP violation has been discovered, which was something happened also in 1964, and the Big Bang is established now that the microwave background has been found, the grounds are now ready to be able to explain the existence of matter over antimatter in our universe, then matter-antimatter asymmetry, often called baryon asymmetry. He remarks in the last paragraph of that lecture notes that it should now be possible to actually work this out. At this point, I jump ahead and come to the 70s. The Big Bang and grand unification connection, in which also he played a major role, because we will see other things, his general relativity, his the popular book and so on, we will come later. But on the technical front, other than his early observation that baryogenesis had become possible, he was caught up in this exciting development that the gauge theories were around, he was inventor of one of them. The gauge coupling constants, the way they ran, the right side panel shows the fine structure constants, that is alphas, for the three disparate forces we see at low energies, the electromagnetism, the weak interaction, and the strong interaction. Their fine structure constants inverse, whatever is shown here, they actually quote run, they change, they have to be scale dependent. This was the big discovery of quantum field theory in the early 70s, the running coupling in gauge theories. So if the gauge couplings were going to grow weaker, the non-abelian gauge forces, and electromagnetism would get slightly stronger, then eventually they would all come together. Of course, the running was very slow, it was logarithmic. So on the x-axis, we see logarithm of the energy scale at which the theory is being explored. And it was about 10 raised to 15 GeV. This is stupendous number, but that's where the couplings would come together. Now, this was really a breathtaking realization because the gravitational constant, Newton's constant, expressed in the particle physics units is 10 raised to 19 GeV. So this was a few orders of magnitude shy of that largest scale we know, beyond which we don't know any physics. So suddenly, within a span of 5 or 10 years, physicists had straddled psychologically the scale from just doing atomic and nuclear physics to scales that reached into the Planck scale. And Georgi and Glashow therefore proposed the grand unified theory SU5, which, just for your information, has not been confirmed. It's probably not correct. Nevertheless, it was a giant step in understanding of fundamental forces. And at this point, Georgi, Quinn, and Weinberg wrote a very clever paper showing how to calculate these trajectories. All of us who are today engaged in doing RG running, the Adi paper of that is this paper, that they come together. Of course, RG was calculated by others as well. And an interesting corollary of this was that proton would decay. When the forces all unify, there are new forces, gauge forces present, and they would allow proton to decay into leptons, the heavy particles to decay into the light particles. And that brings us back to our story of baryogenesis. But before that, so this connection that the straddling all the energy scales up to Planck scale, and that this would actually unfold in the early universe, was epitomized in this picture by some version of the original picture that Glashow made popular. This snake is called the Ouroboros. It is some Norse mythology, where the world is actually supported by a snake which has made a circle and it eats its own tail. So here, the implication being that we are at the largest scale, this mouth, and then we, from observing the largest scales, galaxies, and then solar system and so on, and us here, and ants, and then go to smaller and smaller regimes. Eventually, the tiny regimes take us back to the extremely high energy scales at which all of physics was one fireball. So this big connection came into existence. And here is the consequence of that baryon number violation. And Weinberg's original remark that now it should be possible to dynamically calculate baryon asymmetry of the universe. This was concisely captured in a paper by Weinberg in 1978, because that's the one I read. The criteria are now known as Sakura criteria of 1967, remember Brandeis lectures in 1964, but Sakura wrote a very seminal paper in 1967 where he outlined these. But the way it is written here is essentially Weinberg's 1978 paper. What is required is that baryon number has to be violated, and charge conjugation must be violated, so that X bosons decaying into QQ is not the same amplitude, not the same quantum mechanical amplitude as the antiparticle decay into Q bar. Now, so that some asymmetry has to be built into the theory, and those asymmetries were slowly beginning to be revealed. So it was possible to get this, but it was also necessary to have CP violation, which triggered Weinberg's 1964 remark that the rates, because CP gets tied to the time reversal, the rates for X decaying into QQ should not be the same as X bar decaying into Q bar. So the R1 rate has to be unequal from R1 bar. And what Weinberg remarked once in the lecture class that he took was that although Yoshimura had written the earlier paper, Weinberg's contribution was also to point out that you had to get CP violation, you needed something imaginary in the, and that would not come in the rates if you just had a matrix element squared. But if it was sum of several matrix elements squared, then the cross terms were likely to have a imaginary unit in them, and therefore lead to a time irreversible effective Hamiltonian. And then you need the out of equilibrium conditions for all this to unfold, because otherwise, if it will equilibrium, then if you overproduce the final product, there is more of it, so it will be driven back, although its rate is smaller, and so on. So you need the universe to be expanding away so that what gets produced doesn't have time to recombine back to the original products. So these were worked out by several people, but Weinberg, one of the eminent one and one of the leaders of that group. And I am taking at this point liberty to repeat what Sri Roop may have already shown in 3 slides. These are the proud recipients of the 1979 Nobel Prize for the Standard Model of Particle Physics. And the antecedents of it go back to discovery of the fact that the whole standard model is chiral. It's left-handed fermions and its right-handed fermions have different charges. The discovery went back to this realization by Yang and Lee that this should actually happen. And a brave Madame Wu, who did the experiment in record time, once she learned the idea from these people, and they of course encouraged that it should be done. She did it within 9 months or something like that, less than a year. And then Marshak and Sudarshan realized that therefore the structure of the weak force had to be of the form V vector minus axial vector, which became the cornerstone of the electroweak unification. And I just wanted to emphasize that this itself earned Weinberg a major place in the canons of physics, because this unification by these people was equivalent to Maxwell's unification of electromagnetism, because they put together the weak and electromagnetic force. Okay, so I think I have covered most. The part that I wanted to speak most clearly about was baryogenesis and the big connection between cosmology and elementary particle physics that happened because of the grand unification ideas. These were really the most exciting times. And there are many other things that I hope that I will cover now in the next slides. So if there is any question, please let me know. I could take one at this point. So
are there any questions from the audience in lecture theater? You can directly speak up to the through the speaker. I think there are lots of students sitting there. Are there any questions? Okay, I don't see Urjit.
Okay.
Maybe you can go ahead.
Yes, I will go ahead. So as a student, when we were trying to learn general theory of relativity, and many of, I see my friends of my generation who must have also read Weinberg's textbook. Weinberg brought a fresh perspective. Weinberg's book appeared in I think I have its picture later. This book, which many of you must have now seen. This book appeared at the same time as two other eminent books. One is Misner, Thorne and Wheeler, and another one is called Adler, Bazin and Schiffer. However, Weinberg's book was directly oriented to particle physicists in some sense. But I would not say that it was oriented to, it was really much more oriented to phenomenology of general relativity and taking a down-to-earth stand on what the theory should be understood as. The early developments had created this exciting, I still think it's exciting, it's not, and also would Weinberg agree, I don't think that you would disagree with this, that the emergence of curved space-time as a beautiful and elegant explanation of how gravity works, but created the dream that maybe geometrical picture will displace dynamics. You know, you didn't need a different schema like in Newton's case of dynamics against trajectories, because now trajectories were directly determined by curved space. And then there was the proposal of geometrizing even electrodynamics, a prospect that has not yet been realized. But Weinberg took the approach in this book that general theory of relativity is nothing but the relativistic theory of gravity. Ultimately, it is a force like electromagnetism or any other. It is just that it has certain properties which allows us to think of it as geometry. But this is how one should look at it. And he had so I will say a bit more. I think I have some quotation later. He had similarly the opinion that relativistic quantum mechanics has to be same thing as quantum field theory. You cannot have a theory of relativistic wave equations with wave function interpretations and so on. If you got to relativity, you had to do QFT. There was nothing else to do. And we have to remember that in the 60s, there was sort of a big negative spell cast on quantum field theory by L.D. Landau, who had grown disillusioned with QFT and running of the electrodynamic coupling constant. But Weinberg somehow seemed to have a great faith in QFT at that time. And he worked on this idea that quantum theory of massless particles implies what we now call gauge invariance. So the elegant geometric picture actually is tied very closely to a consistent S-matrix theory of massless particles. And so this is where he was rooted, and this is why he wanted to dispel the idea that you must buy into a geometric picture first and then learn everything. And so coming back to general relativity, he wanted to think of it as a classical field theory, but with a gauge invariance. And the gauge invariance is what actually originates from consistency of the quantum field theory for massless particles. Of course, the logic goes both ways. So it's not as if we are undermining any one view against the other, but the predominance of geometric point of view was in a sense challenged by the way Weinberg presented it in his book. And he does say at a particular point in the book that geometry is essentially an analogy by which we can understand the workings of Einstein's theory. And this was the famous book, this is. And his rather, so the upper half, these are two different pieces out of the preface to that book. One part complains about, I found that most textbooks, geometric ideas were given starring roles, so that a student who asks why gravitational field is presented by metric, etc., felt that space-time, Riemannian manifold is the important thing. And this is what he was trying to dispel. The other thing was that he wanted it to be connected to observation. And so he says the important thing is to be able to make predictions about images on the astronomer's photographic plates, frequencies of spectral lines, and so on. And it simply doesn't matter whether we ascribe these predictions to the physical effects of a gravitational field or curvature of space and time. So, and of course, it says in the parenthetically, the reader should be warned that these views are heterodox. And his stamp of actually being completely engaged with nature, with phenomena, is shown nowhere more strongly than in this particular table that he has in that book, which is the summary of measurements of background radiation flux, the microwave background, which had been discovered in '64, and now this is what, about 7 years later, 6 years later. He sits and collates every single experiment that has observed this and the effective temperature they've observed for it in this right column, which is approximately 3 Kelvin. And all the references for each of the experiment. The thing here to see is, because this is from a time when you didn't have big tech, okay? So that there are also bibliography entries that are J, J prime, K, K prime, probably because they were inserted later because of the right place they had to be. And so this is how, but he painstakingly gathered all these things. And there are many other such tables in that textbook. Later in life, and now we are actually jumping back, but since we are talking the exposition and taking a position on a subject and connected to cosmology, this is his 2008 book on cosmology. By the way, that first book did not have any second edition or any corrections. It remains a classic. Everybody knows it is from the 70s, but all the theory developed, the points of view developed have remained intact. There has been no need to revise it. Of course, the observational aspects went far ahead. And so this cosmology book does this. Here, his aim was to put in place a mathematical derivational framework for working out the implications of the cosmic microwave background radiation as arising from fluctuations, primordial fluctuations. And the whole book is devoted to just that, which in the astro community, of course, because they have to get results, they have to move on. They are not going to sit working with equations. But he wanted to develop the framework mathematically, analytically. And so at some point you find him remarking, the results obtained so far are repulsively complicated, fortunately, etc., etc. So, and this kind of lament occurs at 2 or 3 crucial points in the whole book. I ended up reading the whole thing during lockdown. And it's quite refreshing that to see him just work through the whole thing. Just everything is derived, crystal clear. There's nothing left to imagination. That can be worked out is worked out. And this is also going back down the memory lane to the time when we took his classes. His famous quantum field theory books didn't become books until mid-90s, but back in the 80s, he had been teaching this course even earlier. So this is the front page of one of the handouts. He would be teaching, and every 3rd or 4th lecture, a chunk of sheets would come as a handout where all the notes would be written. And on the right side is a typical example of how the notes would look. Okay. So that sort of covers his approach to general relativity and cosmology, his contributions to bringing together the field of particle physics, the techniques of quantum field theory, and the early universe, all of them together. It has now grown into a subspecialty called astroparticle physics, with his pioneering contribution to baryon asymmetry, which incidentally till date remains a nice benchmark against which to check any theory we have, because no one theory seems to explain it uniquely. So this is about science outreach and opinions. I could have said popular science, but as I'm going to try to argue, he tried to not be too popular. This is his first classic book, The First 3 Minutes, and I searched till I found the jacket of the original print. And this is a very interesting book because what it tries to bring forth, and I would like to share this physics for those who don't know it, that he makes up why is focusing on the first 3 minutes. Actually, it is long. I mean, later understanding says it has to be a longer time, but it's good dramatic statement anyway. The primordial soup, whatever there was earlier, well, quarks and gluons, they cooled down and then first formed the neutrons and protons. These would begin to fuse into heavier nuclei, right, as the gas cools. Now, if that happened, then the fusion could have continued for a long time and could have produced all kinds of metals and elements in the primordial soup, from the primordial soup itself. But there was a very crucial natural thing, which we are still till date are trying to understand why it is true. But we parameterize it by the baryon and photon ratio, baryon to photon ratio, that is proton, neutron together, that is baryon. It turns out that there is only a minuscule excess of baryons, parts per billion, compared to photons. So any heavy nuclei that are trying to form are blasted off. And so the only things that end up forming out of that Big Bang is helium, which is the stablest of the light nuclei, and almost nothing else. Everything is in minuscule numbers. Okay, so it's just hydrogen about 90% and helium about 7% or so, and everything else is less than 1%. This has to do with this remarkable baryon to photon ratio. And this is what he tries to bring out in this book. And therefore, the universe remained largely just hydrogen and a bit of helium. And that is why over the next millions and hundreds of millions of years, slowly galaxies evolved. Because if the fusion had all gone very fast, then heavy elements would have formed and they would not have formed glowing stars. But we have this glowing stars because of this peculiar number, the baryon to photon ratio today. And I have picked here just the last page of this book, the concluding pages of the book, where he goes on to say, the more the universe seems comprehensible, the more it also seems pointless. So this is rather deterring, but that's the way it is. And he doesn't mince his words. And later on, in a poetical or philosophical tone, he says, so if really the world is this vast universe, which can be all explained by these inanimate forces and their internal consistency, then is it really worth studying? And then he says the effort to understand the universe is one of the very few things. So what understanding we gain may be a bit confounding, but the process of understanding is what is the exciting thing. So the effort to understand the universe is one of the very few things that lifts human life a little above the level of farce and gives it some of the grace of a tragedy. This is sort of a showcase of then he was on a roll. He kept writing popular science books. He also wrote a variety of textbooks, which some of them are here because I just harvested this from various Google searches. So you see here lectures on quantum mechanics. This is the classic gravitation and cosmology book in a jacket, which is now popular in Indian edition, paperback edition. But you see the other things like to explain, well, Dreams of a Final Theory is a sort of a focused book. I think these are essays, explain the world. Similarly, Lake Views are other essays, Facing Up and so on. So he was giving lectures continuously at various places, trying to advance the idea of dispassionate exploration of science. He also had a book, Glory and Terror, which is about nuclear weapons and why there should be it should be kept under civic debate and control. And then a few words about, he did speculate like most of us would like to do, but with a couched in good scientific backup. So he did work on string theory basics. He tried to understand it. He has a full course. He gave a one-year course on string theory, which is one of those scrawled pages was. He never published it because that's an interesting point. I don't know whether he published the string theory book or not. But Joe Kolchinsky from our department did. And so maybe that's why he didn't publish it. And supergravity and extra dimensions, he worked on this. This is what Salam was promoting. I don't know whether I put that joke here or not, but when Salam came to Texas Austin and gave a colloquium, that was the heyday of supergravity. And Salam tongue-in-cheek remarked that D equal to 11, which is what consistency of the theory required, that 11-dimensional 11 was not a number holy to any of the known major religions. And Weinberg later remarked that he had to join into supergravity and string theory because Salam had joined in, and he couldn't be found sitting around if Salam was rushing into a particular field. So he said so. And so he gave that lecture course on string theory. Later, I will talk about other things as well, but he did speculate on the multiverse. I don't know if Sandeep is in the audience, but he and the TIFR group have worked on that aspect of string theory, which shows that a large variety of universes are possible within string theory. And then the question arises, what is the meaning of having another universe if you are never going to access it? But he did take a stand somewhere that I think in the Dreams of Final Theory, that if mathematics deems it right, we have to accept that the unseeable world must be there, right? So the point is, these modern theories where we deduce things from mathematics face us with very strong challenges that scientific temper and scientific approach has always tried to overcome, has had to overcome time and time again, that we do not accept imaginary things, we do not think, fantastic, kalpanic lok and so on. But here he had to agree that even if it is unseeable, if the mathematics deems that it is there, we should accept it. And here is an interesting foray he made. Looked like a foray at that time, but turned out to be really a very dramatic contribution, which was that he estimated the magnitude of the cosmological constant about a decade before it was actually discovered. Of course, he was not alone. There were quite a few people working on the anthropic idea, that somehow the fact that human beings emerge, that the parameters of cosmology had to be such that human beings come into existence. And while this kind of argument has easily the risk of going into the thing where the universe exists the way it is so that we would come into existence. So it is not that justificational part, but Weinberg took the stance that just so that we are here would be not possible if the universe had much larger amount of dark energy, because then it would be accelerating at a high rate, and then the kind of universe we know where the slow cooking in the stars and so on, which can produce eventually life, would not come about. So he just tried to, so that's why the anthropic in the abstract is in inverted commas, and he tries to what is the word, gives a new spin to this anthropic principle. He calls it the anthropic argument. Basically just saying that had the universe been, so he just asked the practical question, if I'm looking out for a cosmological constant, at what value should I look out for? That's what it boils down to. It's not a speculation or anything. Just that if I have to build an instrument, how hard should I work and to what limit should I pitch it to? And he basically says that the answer can be found in the fact that had it not been smaller than a particular value, we would not be around to see it. That's a good phenomenological constraint. Our existence is a constraint on what the value can be. And here is some summary of his dreams of a final theory, that we are essentially still within the Newtonian paradigm. That's what he seems to emphasize. And that he also had positive things to say about string theory, now that a lot of people have both ways arguments. But he then concludes that if string theory does end up explaining everything, then we may end up exhausting Newtonian paradigm of trying to understand natural forces using mathematics. Okay, so how much time do I have? Good.
You still have at least 10 to 15 minutes. Yeah.
Yeah, and so now we come to the more personal aspects, his personality and maybe some of my recollections as well. He was a big crusader for the ethos of enlightenment. And this is enlightenment as was realized by European scientists in the late 18th century and up to next. So soon after Newton, once Newton's mechanics made it clear that so many things were calculable, it changed the idea of, and that planetary motion, that the firmament was some other world and the terrestrial world and so on were vanishing. And so it brought in what we now call the scientific temper and the spirit of inquiry, the evidential nature of our understanding and so on. So he did in several lectures, but this is the one where his picture appears and this is still retained. In 2002, he gave a convocation address where he says he urges the students to join as allies in a movement that is about 300 years old, the movement known as the Enlightenment. So those who so it's also true that Immanuel Kant, about 100 years after Newton, remarked, he actually wrote an essay with the word the Enlightenment in it, in which he essentially captured what we now understand as the liberal and the scientific approach to life and society. And he says there that enlightenment has made the world a freer and gentler place. And through its emphasis on the power of reason and its skepticism about any traditional social, political, and religious ideas. Needless to say, Weinberg's comments may not have gone very well with all the parents in the audience, but this is what he always, in fact, that's what was communicated to me by my friend Cliff Burgess, who invited him to McGill University and where he expressed similar ideas. In fact, I think he very explicitly talked about atheism. And Cliff said that the regents were a bit worried about what the donors would be thinking. But there is another joke about his outspoken attitude to rationalism and skepticism. He was once invited to engage in a discussion about God. I mean, the most engaging discussion you can think of, by the BBC. And the other side was also a very well-known particle physicist called Polkinghorne. But Polkinghorne is an ordained priest of the Anglican Church. So Polkinghorne was arguing and Weinberg was basically diffusing most of the things he was saying. In the end, one of the arguments that usually is there in the arsenal of the theist was, but Steve, a flash of lightning was to come down and chop your head off now, would you then believe in God or not? And Steve Weinberg says, I don't know whether I would believe, but it would cause a janitorial problem on the stage if I became beheaded, got into beheaded state here. So let us see what I have in the personal reminiscences. This is also, of course, very old. I never saw him in this form. I just have this picture. Oh, yes. So here are two of the emails I could find. One, quite an old one, going back to what, April 2006. We were going to have Golden Jubilee at IIT Bombay starting 2007. So we were all trying to rope in, like we had ST Yao visit us during that time. So, and Sudarshan visited during that time. So I was trying to rope in Steve Weinberg. And so here, it went back and forth because he would give some evasive reply saying, no, I'm busy, I have other commitment, this and that. And I just tried to say, okay, you can come even later, it doesn't matter. Finally, he says, dear Urjit, I should have been more open in my previous message. As time passes, I like air travel less and less. And although I do go abroad occasionally, I try to limit myself to a minimum of overseas travel. So I'm not able to commit myself to visit India in the foreseeable future, but I'm very grateful to you for raising this possibility. Best, Steve. And then this lower part is actually just very recent. In 2020, August, he participated in this HAPP Center at Oxford University. What's the full form? History and Philosophy of Science, I think, in some sense. So it's a humanities department within Oxford, and they had a conclave of 3 or 4 Nobel laureates and a few discussants. And there, you can read below my first few lines. There, somebody asked him about why mathematics is so applicable to physics or some question of this type. And Weinberg kept silent until Lawrence Krauss, who was the host, said, Steve, do you want to respond? And Steve said, that is above my pay grade. He did not want to commit to any philosophical approach. So I said, I tongue-in-cheek tried to congratulate him on that, but he doesn't say anything. But then I tried to argue that maybe quantum mechanics has been mystified too much. But he says, thanks for an interesting note. I certainly feel, so this is 1st September 2020. Thanks for an interesting note. I certainly feel, as many do, that the emphasis on the observer presents a problem for quantum mechanics. Only I feel, so I had said, well, Schrodinger cat you can get as in some effective field theory. So he says, only I fear that if the wave function of every detail of Schrodinger cat was precisely known, we would still need interpretive postulates to give it meaning. And I don't know how to frame these postulates without mentioning observers. Now, I don't fully agree with, I mean, I don't really know what is his bugbear, but it was nice to get his frank and straight opinion. And I think when I talk about my reminiscences of Steve Weinberg, I cannot do it without the galaxy of other mentors and teachers I had at Texas. One was John Wheeler, with whom I collaborated for almost a year before I moved out of classical general relativity. George Sudarshan, who suggested to me the topics on which my thesis is based, and we actually did work on a project together. And Joe Polchinski, who helped me out in the final stages of my thesis and wrote me some nice recollectors, because of which I could go to some places. And we also were in department famous for quantum gravity, because Bryce and Cecile DeWitt were there and Claudio Teitelbaum were there. And well, there are a few other jokes here. But maybe I should show this to show that Weinberg was real. He actually did go to buy food. But here are some points I have just made. I don't know how much time is left. Yeah, so maybe out of these, I should just say that this brown bag, the mode in which Weinberg interacted with his students and associates was quite a fixed hierarchy of things. So with faculty could go and talk to him, postdocs, he would go and pick on the postdoc to get into a discussion, whereas graduate students had limited rights in access to him. So you could attend all his lectures and ask as many questions as you like in those beautiful lectures. I attended them for 3 whole years, like 6 or maybe even 7 semesters of lectures of Steve Weinberg, the 2 volumes of quantum field theory and then the string theory. But outside of that, the way to interact with Steve Weinberg was that you join his brown bag lunch seminar. So every Tuesday, you brown bag meaning your lunchbox, you walked into his office, people dragged chairs from all over the place and his office was packed with some 20, 25 people. And then while he's chomping his sandwich, you had to start writing on the board and telling him what it is that you have done. So I did that a couple of times and it was quite an exhilarating experience. So, and that way he knew what my thesis was about. So he was also my thesis examiner. And then he gave me this associateship. I became his postdoc after the thesis. But then I got an offer from TIFR and I was very keen on returning to India. So when the offer from TIFR finally came, I went to tell him that I was leaving. And he looked at me straight and just asked point blank, "Are you sure you want to leave?" And I said, "Yes." Then I said, "Will you remember me?" And he said, "Yes, your thesis is right there along with the thesis of my students, which was people like Cliff Burgess, Scott Willenbrock, and Fernando Prevero." So that was my some of the personal things, and yeah, that's the end of this presentation.
Yeah, thank you, Urjit. Thank you very much. I'm actually now in the lecture theater, and just wanted to thank you. So let's have a round of applause. So, are there questions from the audience here? Not that I can see. Everybody's nodding their heads. Anybody? Okay. Are there questions in the Zoom?
I have a question.
Yes, please.
Okay, so this is not exactly a science question. This is more of a philosophical thing. That anthropic principle, that like how feasible it is to say that we can ask the question because we are here. Like, isn't that kind of a roundabout way of answering?
No. So that maybe I could not articulate it very well, but there's an echo. But the point is, as I tried to say, he's using existence of human beings like a constraint. So how should I put it? If some experiment is to produce protons, or say create positron electron pair, it has to at least reach an MeV of energy. Or if you wanted to produce protons, you have to reach at least GeV energy and so on. So it is just like an energy bound, so that this phenomenon can happen. That's about all. It does not say that in any kind of psychological way or any kind of anthropic way or anthropocentric way that it is because we are here to observe the universe or anything. It's nothing. It's just that this complex life forms could evolve only because of the planetary system that we have, and the planetary systems could not happen unless the galaxies evolved in a particular way and so on. So he just uses it as a immaterial evidence to put a constraint on the energy scale of some other phenomenon. Does that answer your question?
Yeah.
Amol, please ask your question.
So Urjit, So you showed some snippets from Weinberg's, some tongue-in-cheek remarks about his heterodox views, and sometime later about his sort of nihilistic views. Uh, but that's something you perhaps only see in his books, because of course when you read his papers, you find them to be just very clearly written, and none of this tongue-in-cheek thing. Or
Yes.
you perhaps have read more papers of him than I have. So
No, no, that is very true. But the point is the quote, let us correct the word nihilistic. They are not nihilistic. They are, okay, in some sense, they would induce despair if you believed in some kind of grand reality out there. He is basically, you can say it is iconoclastic. It's not so much, yeah, okay. So he's trying to break traditional molds of thinking. But I think that part of the reason it was driven because a particular kind of mindset was taking over in America. You remember that this was also the time that the SSC got scrapped in America. And America started on various global wars and so on. So from a very stable time of, America was probably doing something or the other all the time. But during the 70s and 80s at least, when there was a very strong growth of science in the United States, and SLAC got built up and Fermilab got built up and so on. From that, suddenly this switch, and I don't want, I mean, there are all the, what is it called? Design, the special design. There is some approach to thinking about that something as complex as life can come into existence only if there was a secret watchmaker and so on. So all these ideas were proliferating. And I think he is trying to take an active stand, whereas most scientists kind of smirk and leave that thing aside. He is actively trying to take a stand, and especially trying to tell younger students that you must take a rationalist approach, an evidential approach to everything, including your belief structure and so on. So I think he's, in that sense, positive. I wouldn't say nihilist. And that's what we have to read into that last sentence that I was reading, that it is the endeavor of doing science. It is very enriching. He's not saying that it is, but if you expected that if you had a preconceived notions as to what that would reward you with, those notions have not been borne out in 300 years of science. Nevertheless, just the pursuit of science itself is keeping us, so many of us, excited even now, and we have astroparticle experiments planned till 2035, 2050, all kinds of horizons are being planned. So it has not dampened anybody's enthusiasm. So, but that is what has to be kept in mind, that the reward of science is in the doing of it. And of course, whatever spin-offs that come from applications and improvement in human life and so on are not necessarily the ones we are looking at that point. But certainly any kind of psychological solace of the type that is sought in philosophy and religion and spirituality may not be available. That's what he's trying to say. Maybe you have to look for it somewhere else. He's not against it. He's just saying that is not the project of science.
I was pointing out that such even tongue-in-cheek remarks are not present in his papers. His papers are very straightforward.
No, I think he's that way very professional most of the time. He doesn't want to, actually, I don't think he would have taken these kind of crusader stances had he not felt a little worried about the state that America was going into. And yeah, so his papers are all very, very, very frank and straightforward, and they just remain scientific. He doesn't try to mix any, even any snide humor. Very, very mild kind of passing remarks occur. But that is actually another feature of his whole work ethic. He seemed to dislike cleverness. Of course, he was very clever. But he never liked the secret argument, the clever shortcut, heuristic argument that he always felt that everything had to be worked out threadbare. So his papers are also like that. Everything has to be expressed in symbols and then worked out, and that's the answer. And he always made it a point that the starting point brought it to a level where it was like just doing advanced calculus and trigonometry. Once it was brought down, any MSc student can do that calculation. So when things like topology and all these geometric ideas and so on came, you can see in his books, he wants to bring it down to multivariate calculus. So that's what his approach was. I in fact remember one seminar that Witten gave about the Witten term, the West-Zumino-Witten model as we know it now. And he gave the topological argument. And then Weinberg said, wait, Ed, if I thought this way and that way. So he broke into a little speech trying to boil it down to some effective field theory statement just in terms of fields. And then I don't need this topology, right? And then Witten, of course, smiled at it and went on with his lecture. But that's what he was all about. He didn't like any kind of mysticism or extraneous things to hard, clear thinking.
Very nice. Okay. Questions or comments?
Urjit, can I ask?
Oh yeah, hi Gautam.
Hi Urjit. It was a great talk. So I'm just curious about this Weinberg's lectures which you attended. I'm an absolute fan of Weinberg's QFT books, and the fact that he works out all the steps, and it's impossible, I think, to really teach from these books in one semester and so on. So I wonder whether he skipped some steps, or how did he do it?
Yeah. So I would think that some of the things he skipped. In fact, you will find one chapter in his book called Polology. So this is again his dislike for things that once somebody about relativistic wave equations, somebody came to give a lecture and he said some lecture on Diracology, So yeah, he did skip some of the topics. He skipped quite a few, but at the same time, I think the main thread is exactly what the book is, and he just was very rigorous and very fast. He wrote everything on the board from left to right, end to end. So yeah, I think majority of the topics were actually covered in the class. There were 1.5 hour lectures, which went to 1 hour 45-minute lectures every time. There used to be 11 to 12:30 slot. It ended at 12:45, almost always. And the moment he finished writing, he would rush out of the class because he didn't want to spend time answering questions after the class. You had to ask any question you wanted in the class. But yeah, so I have the whole chunk of notes still with me. And you can find that everything is essentially from there. But he does write, as you see, he does write various kinds of introduction to things, motivational aspects to the, and so on. And some of the technical topics may have been skipped. They were not necessarily all covered. But it's really built up on the skeleton of those lectures only. And the viewpoint comes through very clearly in all of the lectures. You can read the book then very easily.
Wow. Thanks, Urjit.
Yeah.
Okay. Any other questions or discussion? Shirup, you are muted. Shirup, you are muted.
Something, Tishman? Yes. Urjit, back to a little bit to the thread which Amol had raised. I mean, how did Weinberg reconcile, his rationalism and agnosticism or atheism with his very overt Zionism? I mean, he was very openly in favor of this Zionism, Israel, and so on. How did he reconcile that? I mean,
yeah, in fact, I'm remembering some quote of his I encountered when I was preparing the previous talk. I think his, I won't say he was a Zionist, but I think he believed that the state of Israel had the right to exist. That's the basic point, I think. And as I remember even from those times and heard from other friends later, apparently he was, quote, further right of even Ed Witten, and Witten had to kind of tone him down, it seems, on some of his views. But I think Weinberg's problem would start if there was a stand that denied the Israel place to exist there. So he believed that the state of Israel had the right to exist. I think that's where it boils down to.
Yeah, no, that is okay. But he used to also support things like, all the kind of things, insupportable things which Israel does.
Oh, that I don't know. That I don't know.
Okay, but this didn't come up in your. This did not come up in your interactions with him.
No, not at all. In fact, I now remember a particular funny episode. We had a classmate who, I think he went into, kind of started a company, but he was for some time a star student of Weinberg called Jerry Gilbert. And Gilbert came from a family who apparently had escaped Auschwitz. He was the grandchild. And he was very self-consciously Jewish. So he wore a Star of David. And of course, he was very nice with everyone and friendly. But he talked about his Jewishness openly and so on. But as part of that, he once brought violin to the department. And he claimed that it was a Stradivarius. I'm not sure that it was, but he claimed that his father had paid $10,000 for it or whatever. At that time was a big number. And apparently he went to, he opened it, kept it on his desk in our student room. I shared the room with him, so he had kept it. And then he went to Wheeler's office, which was just across, and told Wheeler, Professor Wheeler, I have a very special violin. And then, to cut the story short, Wheeler comes over and Wheeler, of course, plays the violin. So he tries to pick up. And Jerry says, wait, Professor Wheeler, it's a very precious violin. And Wheeler backs off. And then he goes and tells the same thing to Weinberg. And then Weinberg, of course, cannot even be approached because his door is always shut. So Jerry, knowing it, lugs the violin and goes to Weinberg's door. And then Weinberg opens it and says, yeah. And he says, I have a very special violin to show you. And Weinberg's reply, quoted by Jerry Gilbert to us, was, thanks, Jerry, but I know beans about fiddles. Slam. Shut the door. So, but I do know that he held Seder, not Passover, but there's one of these Jewish festivals. And Jerry Gilbert certainly went to that. But in a cosmopolitan way, I think. I don't think it was a very religious way that he was holding that. But yeah, I agree with you that there is some what should I say, gray area there. We will not now understand what exact position he held and how because apparently Witten is more liberal than what was his stance. So yeah, I mean, there is something tied to origins. At the same time, that never showed up in his interactions. Another thing that I remember is once somebody came to the brown bag from, this Townsend and this British people were there, Chris Pope and so on. So somebody came who was or somebody cited a paper by P. Smith. And so he said, who's P. Smith? And the speaker said, Peter Smith. Weinberg said, what's a name like that doing in particle physics? Peter Smith? There can be name like Weinberg, Sudarshan, Zimmermann, but what is Peter Smith doing in particle physics? So he was quite cosmopolitan that way. I don't think he had any hang-ups. But he was quite conscious of his Jewish identity. We know now that he grew up in a particular area of New York, and he went to a school which was also had Glashow and Feinberg, and so I'm sure there are many Bergs in his school. So he obviously inherited some attitudes that he eventually, reconciled with his way of thinking. But I think its basic point is you cannot deny Israel the right to exist. Now, whether it then justified the retaliations that the state was doing and so on, I don't know very well. Yuval Ne'eman was also in our department. I don't remember Weinberg paying any extra attention or having any more friendly relation with him. And occasionally some people who showed up who tried to play the Jewish card, but I don't think Weinberg was much open to any of that.
Okay, okay. Yeah, thanks. That was actually very, very illuminating, because it was sort of surprising to see a person.
I can understand. Yeah, I haven't actually tried to study where exactly he stood or what position he took on some of the events that actually happened. And so
anyway, we are all fans of the physics, so that is ultimately what we say.
Yeah. Thank you. Thank you, Urjit. I'm sorry if you had come from IIT Bombay, we would have treated you for some tea and snacks.
Yes, and cakes. There are yeah.
That remains due for your next visit.
Fruit cake.
Yeah. So, but it would be fascinating to have you here actually, and
yes,
and also again have an interaction with all your friends here back here.
Yes.
So, thank you for doing this lovely colloquium and helping us proceed with the series that we have designed so that we can get some reminiscence of what Weinberg had done. I would like to thank everybody in the audience and as well as people who are pretty depleted now in the room for joining in. And I would like to also mention the support staff in the lecture theater for putting this through, Mr. Ji and his team. And of course, Satyanarayana for putting this through YouTube. YouTube link is working. I've shared it. So Urjit, I will also send it to you again on an email with a formal thank you. So thank you again for doing this.
Yeah, thanks to all of you for organizing this.
Okay.
Thank you.
Thank you, Urjit.
Thank you. Bye.
Yeah, bye.
Bye, everyone.
Shirubda, thank you.
You're welcome. Bye.
Yeah.